Thanks, Alma. Welcome everyone to our AI seminar series. It's my pleasure today to introduce Filip Ilievski to actually give a talk at ISI. His talk is about building robust and explainable AI agents for the real world. So Filip is a research assistant professor at the USC Viterbi School of Engineering and a research lead at the Center on Knowledge Graphs within ISI. He holds a PhD in natural language processing from the Vrije University in Amsterdam. His research focuses on developing robust and explainable neuro-symbolic technology with positive real-world impact based on neural methods and high-quality knowledge. Filip has made extensive contribution in identifying long-tail entities in text, performing robust and explainable common-sense reasoning, and managing large-scale knowledge resources. Over the past 3 years, he's mentored around 20 master's and PhD students and has been collaborating with researchers at USC, CMU, Bosch Reward, RPI, University of Amsterdam, and the University of Lyon. Filip has over 40 peer-reviewed publications in top-tier venues on common sense reasoning, information extraction, and knowledge clouds. He's also been actively organizing workshop, tutorials, symposium, and a special journal issue on these topics. And with no further ado, I'll give it to Filip. Thank you.
Great, thank you, Deborah, and welcome everybody. I hope you will enjoy the talk. I'm looking forward to sharing with you all the work that we've been doing over the last few years on building these robust and explainable AI agents with common sense. To start with, when we talk about the future, we usually imagine these kind of scenarios. We see this very often in movies when movies talk about what the world looks like in 2050. We see these agents, these robots that help us navigate complex information, that do our daily tasks, help us with things that we would maybe find boring or tedious. Maybe entertain us, or maybe help us drive, anticipate the intention of other cars. So in the future, when we talk about AI, we imagine these agents that are that can do a lot of these things that we consider to be intelligent, and somehow they are not. They are still beyond reach today. However, so in the past few years, we have seen tremendous progress in AI. We have seen lots of headlines coming up, and this keeps happening these days. Whenever we open the newspaper, there is something again about how impressive AI is, how AI can generate great images, how AI can generate music for us, and beat humans in all kind of games and all. But then at the same time, every once in a while, when we play with this artificial intelligence, we find that it's really not very robust. Here is Oren Etzioni when he gave a talk at USC in 2020, showing this example where a computer vision system detects this blob of water to be a car. And this is not only a mistake. We all make mistakes once in a while. This is a mistake that shows that machines have no common sense. In some of our own research, we have found many other examples. For example, here we say, hey, GPT-X, GPT-2 or GPT-3, let's say, name something around the house that's often replaced. And then GPT-2 says, well, I think that's like TV, television, furniture, and so on. And some of these things might be correct, some might be incorrect. But the problem is that if we ask GPT-2 to tell us about things that are hardly ever replaced, and as humans, we would expect we would expect a totally different set of answers. However, if you look into these two different sets, we see that the models are not really able to grasp this difference. So in a sense, we feel like, okay, this doesn't make any sense to us. So we see that there is this lack of common sense. So before I proceed, let me define what I mean by common sense. So what I mean by common sense actually here comes from two pioneers of common sense reasoning research. One is Ernest Davis, who says that common sense is the common knowledge about the world that's possessed by every school child and the methods for making inferences from this knowledge. Here we have two different components. One is the aspect of knowledge. So common sense is about having some common knowledge. The other one is about making inferences based on this knowledge. Now the question is, okay, so we talk about this common knowledge, but what really goes there? And here we look into, I looked into John McCarthy's definition, again, one of the people that have spent many years working on this problem in the past, who says that common sense knowledge includes the basic facts about events, including actions and their effects, facts about knowledge, about how this knowledge is obtained, facts about beliefs and desires, and also facts about material objects and their properties. So when we talk about common sense knowledge, we see that we talk about a very wide body of knowledge, including facts, including knowledge about actions, about beliefs and desires. So lots of things come into this common sense knowledge. So to make this a little bit more tangible, we look into, I define here three different pillars of common sense knowledge. So one would be intuitive physics, where we have seen a lot of work in the past, for example, by Pat Hayes or Ken Forbes. We have prior work on intuitive psychology, which is about how people think that other people think. So we have great work on that here at USC by Andrew Gordon and Jerry Hobbs, for example, in the past. And then we have work on common facts, so assembling sources of assembling facts into a joint knowledge repository. Some examples here are Psych and more recently ConceptNet, and some work that we've been doing here at USC. So if you want to build agents that can be robust and explainable and show how to and do that by usage of common sense, we want to be able to do all of these things, but also know when each of these matter in a given situation. So essentially contextualize the knowledge that the agents have. So the research goal that we've been after is, how do we build a robust and explainable natural language agents that can perform well on all different aspects of common sense? So in this case, by robust, we really mean an agent that will not be easily broken when they get into a new situation, but will still be able to perform reasonably well. Sorry, something. Okay. So the first idea these days would be to just use transformers. And before I showed an example why transformers in practice don't seem to always be the full answer to this. But this is something that people have been working with for a few years now, and we've seen some results that are somewhat encouraging as well. So the way transformers work is we have that they have been trained on tasks like predicting on language tasks. They have been trained to predict the next word or assess whether two sentences are compatible. And based on this, now we can take these and we can essentially fine-tune them on all kinds of tasks. For example, question answering tasks, or natural language inference tasks, all kinds of things. And people have done this also for common sense reasoning. So we can take physical reasoning and we can fine-tune this transformer on the training data, and this gives us good results. If we look at the leaderboards, we get a lot of proofs for this. For example, here I showed two example benchmarks. There are many others on which the transformers can be really fine-tuned very well to perform great on this task. The problem with this is that these models are really dependent on the training data. So we have models that, if you want to have a model that performs very well in social reasoning, we need to adapt that model with data that comes from the social question answering task. If we want to perform well on numbers, we have to go to the NumRSense and take that training data. So there is this very strong dependency on the benchmark specific training data. What we've been trying to do over the last few years is trying to say, okay, if we want to have models that can perform robustly on unseen tasks, on unexpected tasks, having this dependency on the training data that's always associated with this task directly doesn't seem like a realistic assumption, because tomorrow we'll have to perform well on something else that the model hasn't yet seen, and we can just not promise to the model to have this training data. So what we said, okay, let's get rid of these benchmark specific training data sets and try to see whether we can take the agent and take some independent source of common sense knowledge and bring the two together and see how far we can get with this. So we've been doing a lot of work on this. Essentially, the overall framework has been that we have been combining large language models with common sense knowledge to perform this open world reasoning and explanation. We have done basically, I think there are two main lines of work that we've been looking into. One goes into the actual improvement of this knowledge itself. So bringing it together, contextualizing it, merging it with axioms, things like this. And we've been also looking into combining that knowledge now with these large language models. And we have a bunch of papers under these different lines of work, some under review, and this will be, I'll be talking today basically about these two streams. So talking about organization of knowledge and talking about using this knowledge together with language models to perform a reasoning on unseen tasks. We also have other works that are on specialized skills, for example, numeracy, that I will not be covering in this talk, but you can contact me if you're interested in those after. So one task that we've been, one family of tasks that we've been looking quite a bit at is the family of multiple choice question answering tasks. So in this case, I show an example here. We have a certain scene with, so the scene describes a stage on which there is a woman taking a seat at the piano. The question here is, what is the most natural continuation of this scene? And the correct answer is that she sets her fingers on the keys and nervously does that. The answer is not that she's in the crowd watching the dancers and so on, because if she's at the stage, she's obviously not at the crowd. These two are disjoint, and the other answers are less plausible for other reasons. So how do we do this in our case? So we looked into different knowledge sources out there. So we found ConceptNet, which is the most popular common sense knowledge graph these days. And ConceptNet tells us, well, I know that pianos have keys and they're used to perform music. So, okay, we find the word piano, we find here, that piano connects to keys. That's useful. Then we go to WordNet, and WordNet tells us, well, pianos are pressed by pressing keys. So now we know that it's not only that pianos have keys, but there is this causal relation between pressing keys and actually playing pianos. Atomic goes into this even further. So the Atomic says, well, in order to play a piano, really the only way to do this would be to actually reach for the keys. And typically you're at the stage, you need to sit at it, and there are a lot of strong feelings involved into this. It doesn't talk about nervousness, but we see a lot of other sort of strong feelings coming up. We have visual genome that has a lot of images of people playing piano, so we can extract more features from this data. And then we have FrameNet that tells us that the performer and the audience are two different entities in this scene, which means that for example, option 3 here is incorrect. So the point being that that in order to perform this kind of common sense reasoning, there is hope of doing this by looking at external knowledge bases. However, neither of these sources by themselves seems to be sufficient. So, and we looked deeper into this. So we, this is from a tutorial that we gave a few in 2021, where we categorize these knowledge sources in all kinds of different ways. The point being that they are very heterogeneous. So they use different representations, they use different acquisition methods, they have different knowledge types, different topics, and by themselves they are not really. It's not very easy to combine them. So the first thing we did in order to be able to do anything with these knowledge bases at the same time is we combined them into a single consolidated resource that we call the Common Sense Knowledge Graph, or CSKG. So CSKG combines 7 of the most commonly used resources in the field for common sense reasoning. It's a fairly lightweight integration, so we did not. So for the most part, we actually kept the different levels of representation that we found in the original resources. For example, ConceptNet has words, and Atomic maybe has events which are sort of more specified, that might be ideally linked to full frames in FrameNet and so on. So we didn't go into a very extensive normalization of these, but we did align them as much as we could, both in terms of their nodes and in terms of their relations. And this is a snapshot of what the graph looks like now. So the different colors indicate different sources, and you can see that we get a fairly connected knowledge graph that tells us that is able to connect the different sources together. So I think creating a very good knowledge graph is very important for performing common sense reasoning. But in a sense, we decided to switch the attention from actually towards actually figuring out whether this consolidation is useful at all. So in the first experiment that we did, we tried to do something very simple, but it turned out to be very powerful, of generating questions with our common sense knowledge graph. So in this case, we use the structure of the knowledge graph to sample a very large number of questions from it. So we can create, we were able to create around 1 million questions here that we can then take and use to train our models. The way we create these questions is fairly simple. We take, in this case, just a single hop in the knowledge graph between 2 different entities. For example, we have this statement saying losing weight is used for being healthier. We can lexicalize it, and then we have a fairly elaborate method to obtain other distractors or other incorrect candidates according to the graph structure. And then ultimately we come to something like, losing weight is for what? So basically it's for being healthier, and it's not for embedded software or buying things at store. Obviously this question is not as good as questions that humans would write, but really the power of this is that we are able to create with a very simple procedure. We are able to create 1 million questions or so, and obviously as the graph grows, this would very easily scale up further. So by doing this very simple procedure of generating questions, we can now use these questions as synthetic training data. So we can take these questions and just simply adapt the model as we would do it with any of the actual training data sets, except that in this case, the data is synthetic and comes from this kind of independent source. And so we do that, we tune our model based on this data, and then we have an adapted model that we apply across different test data sets. So in the first experiment that we did, we saw that if we do this, just by virtue of teaching the model to answer these kind of questions, we see that we are able to get a 10% improvement. So for anyone that works in natural language processing, 1 or 2% is usually a very sizable improvement. Having a 10% improvement is, much better, obviously. So this is something that we were very happy with. This showed that we can use the graph to augment the models. But at the same time, we saw that we can get much better performance on some tasks compared to others. Essentially, we saw that on 2 of the benchmarks, we are able to get very, very high improvements, but on the other 3, we were able to get much lower, of 3 to 5%. And so looking closer into this, we realized that there is a relation between the ways these two benchmarks have been created and some parts of CSKG. So essentially there is, these benchmarks have been created by, partially by sampling parts of the original graphs that we included in CSKG. So then we did a further experiment in which we tried to investigate the impact of different factors during the sampling of questions, during the training of the models, and so on. And by using a larger model, but also by being more selective in terms of the sampling strategy of questions, and a lot of other details that we looked into, we have a new model that is based on T53 billion, and that can now do much better on these sort of low domain overlap questions. So questions that are really fully out of the knowledge that we have in our graph. So this is encouraging. So here we see that by doing so, we get 11% improvement over the Roberta baseline, but we also get, in general, much better improvement on the low domain and compared to the high domain overlap. So the takeaways of this first part are that we did something where we did something relatively simple. So we took the set of knowledge graphs that we could find that covered complementary common sense knowledge. We consolidated them into a single resource. We use this resource to generate a very large number of questions that we use to adapt a large language models. And then we found that the result of this is an improved zero-shot accuracy, but also better generalization to these unseen tasks, especially to the ones with low domain overlap. So the second part that I would like to talk about is the follow-up work in which we went back and tried to use the structure of the knowledge a little bit more. So here we realized that the knowledge that we have in our graph is really, in a sense, still heterogeneous, because we have different clusters that we can identify we can identify automatically, basically, thanks to the relations in the graph that might bring different that might have different effect on the training of the model. So we have spatial knowledge, we have temporal knowledge, we have knowledge about utility of objects, and so on. And this is all, and we were wondering whether we can somehow use this structure that the graph gives us. So here again, we went back, we looked into a large set of knowledge sources. We surveyed 21 different sources, and here we show the different kinds of information they have about food. It is there is a lot of variance in the kind of knowledge they have. So some of them talk about taxonomic knowledge, some of them talk about comparative knowledge, cooking faster here, or about sort of social implications that restaurant food is expensive, or maybe cold food is considered to be not very good, and so on. And what we also observed is that the different sources have a very large variance in the number of relations that they have. So on one extreme, we have sources like Quasimodo or Wikidata or Visual Genome that have many thousands of relations. On the other hand, we have sources like CentiNet or HasPart KB that have only one. And then many of the popular ones, like ConceptNet and Atomic, have a dozen to a few dozens of relations. So what we did is we, among the 5 of us that are authors of this paper, we sat down and we had an annotation task where we clustered the different relations we find in these sources into a set of 13 dimensions. So here I show some examples. The dimensions kind of grow from simple to more complex. They go from lexical and similarity knowledge, and they kind of move towards spatial knowledge, temporal knowledge, knowledge about quality, motivations, and so on. And this is not to say that this set of dimensions is absolutely correct. This was not our intention. Our intention was much more pragmatic. It was to devise these dimensions now as a way of as a guidance for us to unify the graph and to see whether we can use this to study the different sources, but also to maybe improve the question answering, generalization over the different tasks. So here we looked into different sources in terms of the kind of dimensions they have. We see that sources like Atomic and WebChild have very wide coverage. They cover all of these dimensions. WebChild has a lot of knowledge for them. ConceptNet has sometimes a lot, and in other cases, very small amount of knowledge. And then we have other sources like Atomic, for example, or Rojette that focus on a specific subset of these. So Rojette is a dictionary. It focuses on similarity and distinctiveness, and Atomic focuses on social reasoning expressed through motivational, quality, temporal dimensions. And so we were wondering here whether, if we take these dimensions, whether we can, what this actually means for the training of the language model. So what happens if we only train the model with lexical knowledge versus only training the model with temporal knowledge? Do we see any difference? How sensitive is the model to these different sets of questions that we give it? And so here again, we use the same framework that I showed before. We only with the difference that we now subset the set of questions that we give to our language model by dimension. So if we do this, we went through this process. We generated these synthetic questions again. Here I showed the number of questions that we get per dimension. It varies quite a bit. So sometimes we have hundreds of thousands. Sometimes we have only a few hundred questions here. But regardless, we went ahead and we trained the model with each of these, and then we see that we see something interesting. We see that if we train the model with the entire set of questions that we had, we get a fairly sizable improvement of here we get 20%. Here we get from 47 to 61, so 14%. But the best performance is actually achieved with using only one dimension. And this is interesting because it shows that we can use, if we're very selective with the knowledge that we use and we really know what we're looking for, we can train a model by using much less data in a more effective way and in a more efficient way at the same time. Now, of course, the trick is how do you select this data in the first place? The other thing that we see in this table is that some of the more naive dimensions, like lexical knowledge, for example, still give a little bit of an improvement, but this is very, very negligible compared to the overall improvement that we get with the other dimensions. So now the hypothesis here that we had was that the natural hypothesis is that, well, probably the reason why the model learns so much from temporal knowledge and not very much from lexical knowledge is that temporal knowledge is just more novel to the model and lexical knowledge is much more trivial. So we went back and we reverted this setup. So we said, okay, let's see if we can take the vanilla model and give it this kind of questions from different categories and see whether the model can answer them very well. And here we see a validation of that hypothesis showing that temporal knowledge and quality knowledge, which seemed very beneficial on the previous slide, are very difficult for the model. And then on the other hand, knowledge types like lexical knowledge and distinctness knowledge are fairly easy with the model scoring 77 or 90%, which is fairly high. So the findings from the second part are that we constructed this framework of 13 dimensions as a way for us to study the behavior of the models when they're enriched with this knowledge, but also study the different kinds of knowledge that we find in the different sources. And we see that some sources cover all of the dimensions, and they might do this by having a lot of knowledge or little knowledge about them. Other sources might cover single or only a few dimensions, so have a more narrow focus. But we also saw that training the models with a single dimension is often more useful than using all of the knowledge in downstream tasks, with the caveat being that figuring out which dimension is more suitable for which task is still an open question. Okay, so I have a little bit of slides about narrative understanding. So essentially this would be switching gears, but I would like to say that we've been dealing quite a bit with this, with the idea of having zero-shot question answering models that we can take the common sense knowledge, use that to improve the language model, and then do very well across different tasks. So more recently, we realized that there is an additional challenge when we want to do this for some more complicated tasks, like understanding narratives. So narratives are more, they are typically more complicated. They involve many other phenomena. For example, they require us to employ procedural reasoning. Things like analogical reasoning becomes much more relevant. Imagination, trying to understand the scene, trying to fill gaps, trying to use high-level things and implicit things. All of these are very natural when we deal with narratives. So I would like to talk about 4 recent works that we've been doing, and I'll just brush through all of these, not going too much into detail, but I think these are all very exciting works that we've been doing along the lines of these aspects. So if we take our prior approach that I talked about, so we take our common sense knowledge graph, we combine that with language models. This seems really insufficient for us to understand stories. So if we have a story like this one, Ben was excited to go fishing with his grandfather. They wanted to socialize, but then Ben figured out that this is too disgusting for him, and he still wanted to socialize with his grandfather, so then decided to watch a movie. So the reason why this story makes sense is because both fishing and watching a film are social activities that Ben could do with his grandfather. It also makes sense because watching a movie does not involve the dangers or the disgusting aspects that fishing had. So in a sense, this story is very logical to us as people. But if we take the common sense knowledge graph and the individual relations that we find in it, this is insufficient for us to reason over such complicated structures. So what we looked into in our first work is we tried to combine these with the axioms that Gordon and Hobbs have developed here at USC in the past years, which tell us a little bit, which essentially serve as guiding principles of how we could understand a narrative like this one. So they tell us that, there is this thing called substitution, where you can substitute 2 items, I1 and I2, if, for example, they appear at the same location, or they're used for similar things, so on. And then there is an axiom about what does it mean to be at a certain location, what does it mean to be similar, and so on. So what we did is we took these different axioms and we mapped those to different paths in the graph. So this is preliminary work. It's fairly simplistic. We defined 3 different story types of unmet expectations, alternatives, and object modifications. We instantiated different paths in the graph that we could use to generate stories. And again, similarly as before, we were able to generate a very large number of stories here. So we were able to get 118,000 short stories. So these are really very short. One example here is, this one. So I went to the street corner, there was a mailbox, but it had no letter slot. And then the story ends with something like, I was disappointed, or something of that sort. So obviously this story is fairly simple, but it shows that just by doing something very simplistic, we can get a very large number, again, of synthetic data. And we had a crowd annotation task here to compare these stories to stories that we get from GPT-2, finding the stories that we generated with our method to be much more reasonable, but similarly interesting to GPT-2. So obviously there is a lot more work to be done here to incorporate these two worlds and to generate better stories. But this is an initial effort that we had on story generation. Another way to generate stories is this work that we did that was led by Peifeng Wang, a PhD here at USC, on imagining and verbalizing common sense stories. So here the idea is that we have a zero-shot model that that can take a lot of stories that have been constructed and essentially learn not to only generate the story, but generate this intermediate graph that we use as an imagination. So the point being that, let's say you're given a prompt consisting of, like a dog and a throwing and a catch. And then we have this module that we train to create a scene graph based on this. So the scene graph would essentially imagine the situation that we would like to tell in a story later. For example, we have a throwing event that has an agent being a woman, and it has the frisbee being the thing that's being thrown, and so on. And then there is a catch event that is an antonym of throw. I think that link is missing, but that would be the idea. And then we have catch. The actor is the dog, and the thing that's being caught is the frisbee. So you see how this all comes together. And then so we have this second part that after we generate the graph, we can verbalize it. So we have generated the graph. Now in the second step, we have this this module that can essentially verbalize the graph into a coherent narrative. And if we compare this to other sources, to other models that exist out there on the task of story generation, we get fairly good performance. So please check the paper for more details, but this is just high level introduction to this effort. So the other thing that we try to do, and this is work in progress, we are preparing this for AAAI, and we have something similar under review at Colin, which is to try to understand narratives by modeling procedural knowledge. So we have a narrative that talks about, here, for example, about an egg and about Amy and about the stove. As we read through the narrative, we want to model, that, for example, here the stove is turned on, that the egg is already cracked. Obviously, as people, the understanding, keeping track of the state of the different entities is very important. And here we also look into the event causality. So what does it mean to heat up a pan? What does that really entail, for the future expectations for this story? So, okay, so this is, what we try to do. We have this, again, a zero-shot framework where we use things like knowledge augmentation from a common sense knowledge graph. We also use different strategies of knowledge augmentation based on other tasks that we can find. And then we have this this method that is able to understand narratives by looking into the attributes, the states of the entities, but also trying to predict, whether there is a conflict between two sentences. This is in order to find stories that are not logical, and then to classify a story in terms of how plausible or how logical it is. So we have good performance with this on kind of in this zero-shot knowledge transfer setup to both story tasks, but also to question answering tasks, to natural language inference tasks. So different tasks that we think would benefit from this narrative understanding via procedures. And the final thing that I would like to talk about here in terms of this kind of narrative understanding body of work is a work that we try to do with where we try to understand narratives through analogical reasoning. So, analogical reasoning has been very well studied in cognitive science. There have been lots of works that have been trying to apply these to various tasks. Applying this to narratives, from what I can tell, hasn't been done, at least not in much detail. So we looked into what does it mean to understand fables through analogy. So we know that there are basically infinite number of fables out there. For example, Aesop fables, but the number of points that they're trying to make, the set of morals, is really limited. We can have one story talking about a merchant that tried to chase an ass, and that causes the ass to run. And we can also have another story about tiger chasing a rabbit, which causes the rabbit to run. These two stories are analogical, and maybe they have a similar point, being, let's say, that you should know yourself and know your worth, or whatever the morals are. But on the surface, these stories are very dissimilar. So we try to capture this by introducing these different dimensions of analogy, going from shallow attribute or deep attribute analogy all the way to morals and purposes and all kind of structures. And we try to do this with off-the-shelf models that we could find for understanding stories and for encoding text, both based on language models or based on frames. So far, we haven't really seen a clear model that can a clear convincing argument, convincing evidence that this can be really done with the methods that we could find. So this is something that we are continuing to work on and trying to see how we can connect stories better. So the takeaways from this third part is that we can use axioms to associate paths in the knowledge graphs to generate stories. We can use language models together with all kind of training data to generate scene graphs and to learn how to imagine and verbalize stories. We looked into transferring procedural knowledge, and then finally into analogy. The reason why I'm showing all of these different components or all of these different streams of work is because I think that understanding narratives is likely a combination of all of these different components, and in a sense, it's a much more complicated task to crack rather than the more simpler short questions task that I was showing before. Okay, so just to conclude, I started this talk with the research goal of trying to build robust and explainable natural language agents that can perform well on different aspects of common sense. We looked into different, going from having many dataset specific natural language common sense agents to building this framework where we combine large language models with common sense knowledge. All of the work that I was talking about, it was really either about consolidating, organizing or enriching knowledge, or combining that knowledge with large language models. So I think we've done quite a bit of progress over the last 2 years, but I would say that obviously we are not there yet in terms of the initial use cases that I motivated this talk with. We cannot have robots helping us clean at home or make food or entertain us. And so I think this this transfer results are useful, but the next step would be to specialize the agent that we have built for different domains. So we have 2 projects in which we are working on this that that have recently started, are in an early stage. One of them is about building social assistants with common sense.
Filip, you're not connected to the mic.
Hi, can you hear me now?
Yeah. Sorry. Can you hear us? We can hear you now. Can you hear us?
Sorry, Deborah, can you speak again?
Can you hear?
Oh, yeah, sorry. Okay,
Okay, perfect.
you can hear now. Sorry, there was an interruption, technology glitch, sorry. Okay, so I heard that, so Ulf mentioned that that I was not audible though over the last minute, so maybe I'll go back to this. My point was that, I started the talk with this question of, how can we build agents that can help us do our daily chores, do things that we find tedious, or maybe enhance our life or entertain us. I showed a lot of different efforts that we've done towards building agents that are robust and that can explain their decisions by the virtue of this integration of neural language models with common sense knowledge. But obviously we are not at the stage where we can just apply this technology directly to these different use cases. So I think the next step would be, one of the next steps, a critical next step, is to take these agents that we have developed and specialize them for different domains. So we have two works that I would like to highlight here that are just starting up as of very recently. One is using social assistants one is trying to build social assistants with common sense that can assist, for example, elderly with Alzheimer's. And the reason why I think this is a very important project is that current assistants do not possess this common sense capability off the shelf. So I think we have to, in order for these assistants to be really useful for these populations, we have to take another step to adapt them to make sure that they have this common sense, this ability to be robust and to be explainable and to be able to understand the intent of people and so on. So here is a very high level intuition of how that would work. So let's say we have a situation where we have a person that feels cold and there is no blanket nearby. We can have, ideally, we'd like to have an assistant that has this chain of reasoning that says, okay, I know that feeling cold is an uncomfortable state, and when people feel cold, they tend to strive to get warm. And so I know that there is no blanket nearby, but I know that jackets have a very similar function. So the assistant then could suggest, well, why don't you just use a jacket to warm up? And this is a trivial example, but it is something that you can imagine would be useful in similar in a lot of different situations. And common sense is really the key. Here are some of the components that I think are very critical for this to be really achieved. Another use case, which is very different, but I think where common sense also plays a very important role, is traffic monitoring. So, if we have an image like this one, we can have a computer vision system that tells us, well, I see a van and I see, a lane I see a road and I see a bicycle path and so on. But the system won't really tell us that, well, there is a parking violation here because the van really shouldn't be on the bicycle path. So again, we can apply some chain of reasoning that relies on common sense knowledge. It also relies on other aspects, especially in this case, like having more domain knowledge, having expert knowledge. I think it's also a very important component. And then we can ideally have a system that knows that this is a parking violation. Okay, so that's all that I had for today. If people are more interested, we have a bunch of events that we have organized or participated in over the last 2 years, workshops and tutorials. There is a USC symposium from the end of last year that we organized. So please check those resources. All the recordings are available. And with that, I would like to thank you all for listening, and also I would like to thank my students and my collaborators. So a lot of the work that I presented has been, guided by a lot of these people, and it has been done in collaboration with them. So I would like to thank them as well.
Thank you for a great talk. I'd like to open it to attendees first if you have questions, or panelists. So if you're an attendee, use the Q&A features. If you're a panelist, please raise your hand or open your mic. All right, well then I'll start. One of the question I had is, this looks like the common sense is pretty basic, but is there like a cultural bias in how you're doing this, and how do you address this?
Yeah, thanks. That's a great question. So there is, I think there is a very strong cultural component in the common sense knowledge sources that we are looking into, and I think also at the tasks that we are trying to solve. There seems to be more of a pyramid of a sort, where a small set of the knowledge is probably undisputable. Things like, if it rains you get wet, perhaps more things like physical reasoning and so on. But already things like whether whether black color is used for mourning, or these things already become much more cultural, and many of these sources have been created in the Western hemisphere, so we really see a lot of the bias that comes with it. We have done some work, in fact, Jay Pujara and Fred Morstatter and Nina Merabi at USC and Pay. Okay, so that was a team that had been working on this last year, and we had, together with Fred, we had a follow-up work where we inspected the amounts of bias and also the sources of bias in these models that we've been building. We found a lot of them, and we tried to quantify this. But I think the way forward is also not very clear to me personally. So I think it's a very complex issue to deal with.
Thank you. So there's a question in the Q&A. I'm going to read it. Do you see any space for improvements in terms of evolution of models, learning common sense reasoning?
Oh yeah. So I do. So I think that in a sense, we started this enterprise with looking at this multiple choice question answering, because that was kind of the most tangible task to start with. And we are now as I mentioned, over the last year, we've been working towards understanding of narratives by using all these different mechanisms. I think a logical next step would be to look into more embodied tasks, into games that could be text-based games, could be multimodal games, simulations, things like that. So a lot of and these tasks are, I think, starting to come up, and we're starting to work on this basically this month on tasks that involve kind of understanding in text-based games, performing missions, understanding goals in these kind of settings.
Thank you. I think Ulf was next.
Yes, very interesting talk. Thank you very much. How language specific is your work? So a lot of the resources are English based. What would it take to make this work for Dutch or Macedonian?
This is a great question, and I have to admit I have not considered this in the past. I'll try to give a fair answer to this, but I think we should actually keep talking more. I think my initial response would be that, first of all, yes, this is true. Like all of the work that I presented has been entirely tailored to English. The tasks are in English, the resources are in English, the models are in English, the full framework is. I would say that I think doing this for other languages is possible, but it would probably take, it would mean a rethinking a little bit the full architecture and likely the approach. I'm also not an expert in linguistics, so it could be that doing this for Dutch or for German or for Romanian or something, or Macedonian, would take quite a bit of, maybe it involves other phenomena that we have not anticipated yet. So yeah, I think that's something that we should discuss.
Thank you. Looking forward to a good conversation.
Me too.
A couple of more questions in the Q&A. The first one is, can you explain how you use common knowledge in helping GPT-2 to improve its performance? You mentioned the common knowledge database can generate a lot of data for training. I wonder if there is a better way to integrate the common based knowledge of logic and rules instead of pure data samples.
Okay, so I think that's a good thing to wonder. I think we're wondering about the same thing as well, to be fair, David. I think that we tried a simple approach and this worked. We tried to do this also in other settings. We actually started with supervised setting and eventually gave up on this because I think we found the zero shot to be more interesting and just less explored. But I think there are a lot, in general, I would say there are two families of methods that people tend to look into. One would be taking the knowledge graph and trying to inject that knowledge into a language model, which is, which is what we try to do. I think there are variants of this strategy, but I would say what we try to do is fairly representative. The other option would be to do this, to do decision making on the graph itself. So to create a subgraph and to try to produce a decision. And this is something we have not worked with ourselves. We have some of the partners at the Machine Common Sense project from Stanford have been working on, using graph neural networks to do this. However, I think that work is, again, primarily supervised. So it's using, using the training data of the task to do this. I think this is a very good question. I think also in terms of the axioms, we did something very simple where we took the axioms as a guiding principle to create paths. This doesn't scale off the shelf. So how to do this automatically, how to ground axioms in the knowledge graph. It's an excellent research question to pursue, and it's something we haven't done yet. And then, okay, yeah, I think that's my answer to that one.
Thank you. And the last question I have for you is, have you tested with longer or more involved stories yet? No,
we have not. Yeah, this is on our list. We want to do this soon. There is a task that we were discussing a couple of months back where people have used. So most of the story tasks that we have been working with and that I think the community has been working with have these typically around 5 sentences tasks, which are, they're kind of short. And there is a new task that people have proposed that we're discussing that has a few that basically has stories that span a few pages. So that would be already quite a large step towards this. We have not tried it. I'm very curious what happens.
Thank you. And actually got one last question. How much of the focus in the research should be on creating data for common sense tasks, because common sense task is very domain specific?
How much? Okay, I think that's I think that, well, I don't know what you mean with common sense task is very domain specific. I think, we tend to think that much of the common sense knowledge really is sort of more general. Obviously, there is a lot of layers that come into play here. So if you look into, domain of traffic or domain of medicine, there is further knowledge that is probably considered common sense in that domain. And that's certainly something that, I don't know what's the proportion of those layers to each other, but I think there is something there to be explored. How much of the focus? Well, I think in our work, from what I presented, we typically split the focus between the two. I think we spend a lot of effort in actually trying to get high quality data, trying to get data that we can trust, or at least know the limitations of, and knowing what we cannot do with it also. But I think in our case, in most of the frameworks that I presented, there is also the aspect of how do you connect this data to the model, so the aspect of neuro-symbolic integration, and that's very important too. So I think in our case, I would say we split the attention between these two parts quite a bit.
Thank you. And with this, let's thank Filip again for a very interesting talk, and hope to see you all next week for our next seminar.
Thank you.